Many processes are reversible, and for example the vaporization and condensation of water, where we have a sealed container and water molecules escape due to vapor pressure, and at the same time some molecules condense. An equilibrium is reached when the rate of evaporation is equal to the rate of condensation. And another example is a sparingly soluble salt, but if you add excess silver chloride to water, then the solid dissolves, and at the same time the ions combine to produce an equal amount of solid. An equilibrium is reached when the rate of dissolution is equal to the rate of precipitation. So the main point is that when equilibrium is reached, the reactants and products are both present, and the molar concentrations or partial pressures of all species remain constant. And the equilibrium state is dynamic, meaning that the forward and reverse processes continue to occur at equal rates. So the processes don't stop occurring, and this results in no net change that can be observed. We can use graphs of concentration, partial pressure, or rate of reaction versus time to understand when chemical equilibrium is established for simple chemical reactions. So here we have the Haber process, which represents the industrial production of ammonia from nitrogen and hydrogen gas. So for every mole of nitrogen that's consumed, 3 moles of hydrogen are consumed, and 2 moles of ammonia are produced. So before equilibrium is established, there's a change in concentration of the reactants and products, and when equilibrium is established, the concentrations remain constant. And here we can observe from the rate of reaction versus time, before equilibrium, the rate of the forward reaction and the backward reaction is not equal, but when equilibrium is established, the rate of the forward and reverse reactions are equal. So while the concentrations are constant, they're not necessarily the same. And the forward and backward reactions still continue to occur at the same rate. When equilibrium is established, the rate of the forward reaction, which you can write in terms of the concentrations of the reactants raised to the stoichiometric coefficients, is equal to the rate of the reverse reaction, which has a rate constant of Kb, multiplied by the concentration of the product raised to the stoichiometric coefficient. Now if the rate of the forward reaction is greater than the rate of the reverse reaction, then there's a net conversion of reactants into products. And if the rate of the forward reaction is less than the rate of the backward reaction, then there's a net conversion of products into reactants. So in this example here, the rate of the forward reaction is greater than the rate of the reverse reaction, prior to equilibrium being established. The equilibrium expression for a reaction can be written in terms of the molar concentrations, and take the concentrations of the products in a numerator raised to the stoichiometric coefficient, and divide them by the products of the molar concentrations of the reactants in a denominator. Now if the reactants and products are gases, it's more convenient to calculate the equilibrium constant in terms of the partial pressures. And the equilibrium constant depends on the temperature, because you'll get a different state of equilibrium at different temperatures. So in general, the reaction quotient has the same expression, but it describes the relative concentrations of the reaction species at any time. And the reaction quotient tends towards the equilibrium constant, such that at equilibrium, both constants are equal. And for substances with concentrations and partial pressures that don't change throughout the reaction, such as solids and pure liquids, we don't include their concentrations or partial pressures when calculating the equilibrium constant or the reaction quotient. The equilibrium constant in terms of molar concentrations can be derived using the law of mass action, which states that the rate of a reaction is proportional to the product of the concentrations of each reactant. And it's also been observed experimentally that the equilibrium constant depends on the stoichiometric coefficients. So when equilibrium is reached, the rate of reaction in the forward direction is equal to the rate of reaction in the reverse direction. And therefore if we divide through by the rate constant in the backward direction, and divide through by the concentrations of the reactants, this is equal to a constant, which is known as the equilibrium constant in terms of the concentrations. Now you can also obtain an expression for the equilibrium constant in terms of the partial pressures by using the ideal gas law. And if you divide through by the volume, you get the pressure being equal to the molar concentration by the universal gas constant and the temperature. And therefore the molar concentration can be written as follows, and you'll be able to write the equilibrium constant in terms of the partial pressures of the gases. Write an expression for the equilibrium constant in terms of the concentration. Well, the equilibrium constant is equal to the concentration of the products in a numerator raised to the stoichiometric coefficient on the concentration of the reactants in the denominator raised to the stoichiometric coefficient. And we don't include the concentration of solids or pure liquids in this expression, because their concentrations don't change throughout the reaction. Ice tables are popular for calculating the equilibrium constant. So here you set up a table where you have the initial, change, and equilibrium concentration. So for example, you'd be given the initial concentration of the reactants and products and an equilibrium concentration of one of the products. So therefore you can calculate the change in concentration of product C in this case by subtracting the initial from the equilibrium concentration, and then using the mole ratios we can figure out the change in concentration of the other reactants and product. So for every 2 moles of C that are produced, 1 mole of D is produced, and 1 mole of B and A are consumed. So we put a minus here. And then you sum all these together, and then you can calculate the equilibrium constant, and other problems are straightforward. So for example, you may be given 3 equilibrium concentrations and the equilibrium constant and asked to solve for another concentration, or you may be given the partial pressures of gases and asked to calculate the equilibrium constant, and we'll cover some example problems. 2 moles of reactant A and 3 moles of B are combined in a 2-liter rigid container at 900 Kelvin. At equilibrium, 0.5 moles of C is observed. What is the value of the equilibrium constant for this reaction at this temperature? Well, we can construct an ice table because we know the initial concentrations of the reactants. So we have 1 molar of A and 1.5 molar of B. And before the reaction initiates, we have 0 concentrations for the products. And at equilibrium, 0.5 moles of C is observed. So that'll be 0.5 on 2, which is 0.25 moles per liter. And therefore the change in molar concentration of C is plus 0.25. And for every mole of C that's produced, 2 moles of D are produced. And 2 moles of B are consumed. And 1 mole of A is consumed. And now adding all these together, we obtain the equilibrium concentrations, which we can use to calculate our equilibrium constant, which gives the following result using one significant figure. The magnitude of an equilibrium constant gives us some information about a reversible reaction. So recall that the equilibrium constant was the ratio of the concentrations of the products raised to their stoichiometric coefficients over the concentrations of the reactants. If the equilibrium constant is greater than 1, then the concentrations of the products will be higher than the concentrations of the reactants when equilibrium is established, and if the equilibrium constant is less than 1, you'll have a higher concentration of the reactants at equilibrium, and if it's equal to 1, then you'll have equal concentrations of the reactants and products. Now some equilibrium reactions have very large equilibrium constants, which are much greater than 1. So for example, in this first reaction, the concentrations of the products will be much higher than those of the reactants, and therefore the reaction essentially proceeds to completion. And in this third example, the equilibrium constant is much less than 1, so the reaction barely proceeds. And note the dependence of the equilibrium constant on temperature. We can apply different rules to obtain an equilibrium constant for a particular reaction using similar reactions with known equilibrium constants. So we can write the equilibrium constants, for example, in terms of concentration as follows for both reactions. And if we reverse a reaction, we invert the equilibrium constant. So for example, if we do this in the first reaction, then we basically swap those reactants and products. Now if we multiply the stoichiometric coefficients of a reaction by some factor f, then we raise k to the power f. So as you can imagine, by multiplying the entire reaction, we effectively multiply each of these exponents by that same power, which is the same as raising this entire expression to that power. And if we add reactions together, so for example 1 and 2, we effectively multiply the equilibrium constants together. So as you can imagine, by adding these reactions, we'd have all the products in a numerator and all the reactants in a denominator. So we're basically multiplying the expressions together. Determine the equilibrium constant for the following reaction, given the equilibrium constants of the following reactions. So we need to reverse the first reaction to put the silver diamine cation on the right hand side, and in doing so, we need to invert the equilibrium constant. And the second reaction is consistent, so we don't change it. And therefore when we add these two reactions, the silver cations cancel on both sides, and we obtain the same reaction. So therefore by summing these reactions together, we multiply these equilibrium constants to obtain the equilibrium constant of our given reaction, which gives the following result. We can predict the concentrations of partial pressures of species at equilibrium, given the balanced reaction, initial concentrations or partial pressures, and the known equilibrium constant. So here we construct an ice table, and before the reaction initiates, we have 0 concentrations of the products. And the reactant A gets consumed, where X is an unknown concentration, and for every mole of A, 1 mole of B gets consumed, and 2 moles of C get produced, and 1 mole of D gets produced. Then we add these together, and then we write the equilibrium expression using the unknown concentrations raised to the stoichiometric coefficient, and the concentrations of the reactants go in the denominator. And given the equilibrium constant is known, we can solve for x and then substitute into these expressions to obtain the equilibrium concentrations of the reactants and products. And you may get similar problems involving gases and partial pressures rather than concentrations. Determine the equilibrium concentrations of the reactants and products in a 0.1 molar solution of acetic acid, where the equilibrium constant is given. So here we set up an IS table where the initial concentration of the reactant is given, and before the reaction initiates, the concentration of the products is 0. And for every mole of acetic acid that's consumed, we have an unknown change in concentration, and using the mole ratios, we have the same unknown change in concentrations of the products. And then adding these together, and the equilibrium constant can be written in terms of the concentrations of the products on the concentration of the reactant raised to its stoichiometric coefficient. And to avoid solving a quadratic equation, we can apply the approximation that the equilibrium concentration of the products is mostly insignificant compared to the initial concentration of the reactant. And now we can solve this equation much easier. So that's equal to the concentration of the products, and then subtracting from 0.1, we obtain the equilibrium concentration of the reactant. Let's use this particulate level representation to represent the concentrations of the reactant and product particles before and after equilibrium is established for this dissolution and precipitation reaction. And here we can write the equilibrium constant, and here we'll take each particle as representing 1 mole, and the solution will take as 1 liter. So initially, our concentrations of each ion in this solution are 0. And then after some time, we have 1 mole of each ion dissolving. So our concentration of the silver and chlorine ions are 1 molar. And at the next step, we have 2 molar of each type of ion dissolving in the solution. And here we have a backward reaction where the ions bond together to form a precipitate, where another 2 moles dissolve from this solid. And you can observe the remaining concentrations to be constant. So effectively, equilibrium is established at this step, where the rate of dissolution in the forward reaction is equal to the rate of precipitation in the backward reaction. Suppose we have a reaction that's in the equilibrium state, so the rate of reaction in both directions is equal. And we can place a stress on the system at equilibrium by changing the concentration of the reactants or products. And according to Le Chatelier's principle, the system responds to relieve the stress. So in this example, if we increase the concentration of one of the reactants, then the reaction shifts to the right to use up that added substance. And if we decrease the concentration of a reactant, then the reaction shifts in a direction to create that removed substance, which is to the left, or in the direction of the reverse reaction. And similarly, if we increase the concentration of a product, the reaction shifts to the left to consume the additional product. And if the concentration of the product is decreased, then the reaction shifts to the right to create more product. Another way we can stress a reaction that's at equilibrium is by increasing or decreasing the temperature. So if we have an exothermic reaction, we add heat to the right, and therefore an increase in temperature will increase the product, and the reaction shifts away from the increased energy, which is to the left. Now in addition, because a change in temperature changes the reaction kinetics because it affects the rate constant, then the equilibrium constant is going to be affected by a change in temperature. So because here the reaction shifted to the left, then the concentration of the product would decrease and the concentration of the reactants would increase. And therefore an increase in temperature would result in a decrease in the magnitude of the equilibrium constant. And conversely, if we decrease the temperature, so that would result in an increase of the magnitude of the equilibrium constant. And in the case of an endothermic reaction, we will treat the heat being added as a reactant, and I'll leave it for you to think about and verify that the shifts in the reaction would be in the opposite direction to the exothermic reaction. Another way we can stress a reaction at equilibrium is by changing the pressure of the system. So if we increase the pressure on the gases by decreasing the volume of the container, then the partial pressures of all the gases would increase. And because there's more moles of reactants than products in this case, the reaction would shift to the right to relieve the stress, because the partial pressures of the reactants would be higher. Now if we decrease the pressure on the system by increasing the volume of the container, then the partial pressures of the gases would decrease. And therefore, because there's more moles of reactants on the left than there are of products, then a reaction shifts to the left to relieve the stress according to Le Chatelier's principle. Now we can also increase the pressure by adding an inert gas while keeping the volume constant. So in this case, the inert gas does not react with the other gases and won't increase their partial pressures, and therefore there's no stress on this reaction which is at equilibrium, and no shift in the reaction occurs. So only the total pressure of the gases changes due to the addition of helium. We can stress an aqueous solution by diluting it with water. So if we increase the volume of the solvent, then that effectively decreases the concentrations of the reactants and products. So if we have more products, then the reaction shifts to the right in this case to create more products, because there's more aqueous species on the right that lose concentration. Now if we decrease the volume of a solvent, so for example by evaporating water, then we're increasing the concentrations of the reactants and products. And therefore the reaction shifts to the left in this case, which is a side with the less aqueous species, and relieve the stress by consuming more product. So have a think about this. An experiment is conducted where sodium chloride is added to the following solution, which is purple at equilibrium. Will the color of the solution appear closer to blue or pink? So at equilibrium, the cobalt tetrachloride species is blue and the other cobalt complex is pink. And by adding sodium chloride in an aqueous solution, it dissociates into sodium and chlorine ions and thereby increases the concentration of the chlorine ions in the solution. So therefore the reaction shifts to the left to relieve the stress due to the increase in concentration, and will thereby create more cobalt tetrachloride, and the solution will appear closer to blue than pink. The reaction quotient is really a quantitative application of Le Chatelier's principle, and we'll look at a simple case where the concentration of a reactant is increased at a constant temperature. So when the concentration of hydrogen is increased, for example, then the system responds by shifting the reaction to the right. So the excess reactant, H2, gets consumed, and this results in the other reactant being consumed also, while more of the product gets produced. So at our next state of equilibrium, the concentrations of the reactants and products are constant. And similarly, when we look at the rate of reaction versus time, you have an initial jump in the forward reaction, and as the excess reactant is being consumed, the rate of reaction decreases in the forward direction. And then when more product is formed, this is consumed in the backward reaction. And when a system was stressed, there's more reactants than there are products, so the system basically responds to restore the reaction quotient to be equal to the equilibrium constant. A change in temperature can also cause a change in the equilibrium constant. So if we consider this exothermic reaction, we add heat as a product, and using the reaction kinetics, an increase in temperature is going to cause an increase in both the rate constants. But due to the activation energy, the increase in the rate constant in the reverse reaction is going to be higher than that of the forward reaction, and therefore the reaction shifts to the left. Recalling that the equilibrium constant can be written as the ratio of the forward and backward rate constants, well, the equilibrium constant is going to drop with an increase in temperature. And then at equilibrium, these rates are going to be the same and remain constant. Now since there's an abrupt drop in the equilibrium constant with an increase in temperature, then the reaction quotient will be higher at this stage, and while the reaction is shifting to the left, product is being consumed and reactant is being formed, so the system is basically bringing the reaction quotient into agreement with the new equilibrium constant. The rate of forward and backward reaction is plotted below for a reversible reaction. Identify the time when a system is stressed in the equilibrium state, determine if the equilibrium constant will change, and the type of stress. Well, the system is at equilibrium when the rates are equal, so it's being stressed at this time over here, where there's an abrupt change in the rates of reaction. And in this case, the equilibrium constant will not change because the rate of the forward reaction is equal to the rate of the reverse reaction, so there's no change in the equilibrium constant. And if the stress was due to a change in temperature, then the forward and backward reactions will change by different amounts. But since they increased by the same amounts, then the stress must have been due to a catalyst, which increases the rates of both the forward and backward reactions. The solubility product is an equilibrium constant that can be used to determine the extent to which a salt is soluble. So for a slightly soluble salt, the dissolution process is reversible, and the solubility product constant is simply the product of the concentrations of the dissociated ions, raised to the stoichiometric coefficient. Then typically you need to determine this equilibrium equation, and we use the charges of the ions to determine that. So for example, calcium is an alkaline earth metal, which has a 2+ charge, and therefore to balance the charges on this ionic solid, the phosphate ion must have a 3- charge. And when this salt dissociates, we have calcium and phosphate ions in an aqueous solution. And we need to ensure that this equation is balanced on both sides, and the solubility product is equal to the concentration of the calcium ions raised to the stoichiometric coefficient, and we multiply that by the concentration of the phosphate ions raised to the stoichiometric coefficient. To determine the solubility of a substance using the solubility product, we first write the equilibrium equation using the charges in the ionic solid. So we know that calcium is in group 2, then carbonate must have a 2- charge to get an electrically neutral ionic solid. And therefore this salt dissociates into calcium and carbonate ions. And now we can write the solubility product, which is a product of the molar concentrations of the dissociated ions raised to their stoichiometric coefficients. And note that this equation is balanced, and we're given a solubility product, and for every calcium ion in solution, which is unknown at equilibrium, we have one carbonate ion in solution. So this is the same as x squared, and if we solve this equation by taking the square root, so that represents the molar concentration of calcium and also the molar concentration of carbonate, which have a 1-to-1 ratio in the solution. And for every mole of calcium, we also have 1 mole of calcium carbonate. So this here is the molar solubility of the solid. We can use the relationship between the solubility product and the concentration of the dissociated ions of a salt that's slightly soluble to determine the relative solubilities between different substances. So as we can see, for all 3 cases, they have the same number of ions in solution when they dissociate, so we can see that they have similar solubility products. And when we solve for the unknown concentrations of equilibrium, we're basically going to substitute an unknown x and then take the square root of both sides. So therefore, the solubility products that are given here can be used to determine the relative solubility between these substances. So lead-2 chromate is the least soluble because it has the smallest solubility product, which would result in the smallest molar solubility of the solid. Now we know that sodium chloride also dissociates into a 1-to-1 ratio of ions, but it has a molar solubility greater than 1, so it dissociates fully, whereas these above salts are slightly soluble, where the solubility product is less than 1. We can relate the solubility rules that we explored earlier quantitatively to the solubility product. So as we can see, according to rule 1, salts with ions from the alkali metals are soluble in water, and that's indicated by this compound here. And the solubility is typically given in grams per litre, which we can convert to the solubility product to get a comparison with insoluble salts. So we can see that from the second rule, salts with the following polyatomic ions are also soluble. So here we have silver nitrate, which dissolves in a 1-to-1 ratio of silver and nitrate ions. And we can see it also has a solubility product greater than 1, whereas the solubility product for slightly soluble salts is a lot less than 1. Determine the molar solubility of silver chromate, which has the following solubility product at 25 degrees. And using the charges on the ions in this salt, we can write the equilibrium equation. So chromate has a 2- charge, and therefore 2 silvers each have a +1 charge. And this slightly soluble salt dissociates into silver and chromate ions in an aqueous solution. So to balance this equation, we must have 2 silver ions per chromate ion that dissociates. And now we can write the expression for the solubility product for each ion. And at equilibrium, we know the solubility product, but we don't know the concentrations of the silver and chromate ions. But we know that for every mole of chromate, there's 2 moles of silver in solution, and we square this unknown concentration of silver. And this simplifies as follows. And now we can solve this equation. So this here represents a concentration of chromate in solution, and for every mole of chromate, we have 1 mole of silver chromate. So this here is also the molar solubility of our salt. The solubility product of silver chloride and a 15 ml of 0.001 molar of silver nitrate is added to 85 ml of a smaller molar concentration of potassium chloride. Will the silver chloride precipitate? Well, if we write the dissolution precipitation reaction of silver chloride, and what we need to do is determine the reaction quotient when these 2 solutions are mixed together, and if it's greater than the solubility product, then the reaction will shift to the left according to Le Chatelier's principle, and we obtain silver chloride precipitate. So to obtain a concentration of silver ions when these solutions are mixed, we need to first determine a number of moles, and then the molar concentration of the silver ions is equal to the number of moles on the volume of the solution when these 2 solutions are mixed. And in a similar way, you can obtain the concentration of the chlorine ions. The reaction quotient is greater than the equilibrium constant, so therefore the reaction produces more precipitate until the reaction quotient and solubility product are in agreement. We previously calculated the molar solubility of silver chloride in an aqueous solution. Now suppose we add silver chloride to the aqueous solution. Well, this dissociates into sodium and chlorine ions, and therefore by Le Chatelier's principle, that increases the concentration of the chlorine ions in the solution, thereby shifting this reaction to the left, which thereby reduces the solubility of silver chloride, because sodium chloride had a common ion with silver chloride. Now we can quantify this using the solubility product, and suppose we add 0.1 molar of sodium chloride, so due to the 1-to-1 ratio, the chlorine ions would also have the same concentration. And now if we take the approximation that the molar solubility of silver chloride will be significantly smaller compared to the concentration of the chlorine ions that we added, and due to the 1-to-1 mole ratio, this is also the molar solubility of silver chloride, which we can see has been drastically reduced due to the common ion effect. Suppose we have a saturated solution containing precipitate of calcium fluoride and some dissolved calcium and fluorine ions, because it's a sparingly soluble salt. Now suppose we add hydrochloric acid to this solution, which is a strong acid, and thereby dissociates fully in an aqueous solution, which decreases the pH of the solution, which basically means it makes it more acidic. And we'll learn more about acids and bases in the next unit. So here the hydrogen ions react with fluorine to produce a weak acid, and therefore this reduces the concentration of fluorine ions in the solution. And note that if calcium and chlorine ions react, calcium chloride is a highly soluble salt, so these ions will remain dissociated. Now given that the concentration of fluorine has been reduced, by Le Chatelier's principle, the reaction shifts to the right, and therefore the salt becomes more soluble with a decrease in pH. The free energy change, being the enthalpy minus the temperature multiplied by the entropy, measures whether a process proceeds without the input of external energy, and the entropy measures the disorder of the system, and T is the absolute temperature in Kelvin. And generally, nature moves towards low energy and high disorder states. So for the dissolution of an ionic solid, the breaking of the solute bonds requires the input of energy, but the change in enthalpy is positive, and when the ionic bonds are broken, the ions are free to move around, so therefore the disorder or entropy increases. And in step 2, energy is required to separate the solvent molecules, and therefore the intermolecular forces become less significant, and the disorder of the system also increases. And when the intermolecular forces are formed, in this case being ion-dipole interactions, energy is given off to the surroundings, and the system is more ordered. And we'll quantify the free energy for reactions later on.